Hi everyone. In the previous lecture, we talked about the frequency response of opamp based circuits, and we also discussed the frequency response of adders. In this lecture, I'll just uh, discuss a few more points that I felt I did not discuss in the previous lecture, mainly related to opamp based amplifiers, subtractors, and adders. Okay, and some simple techniques to arrive at the closed loop response of op-amp based circuits. And also towards the end of the lecture, I'll talk about the frequency response of a subtractor, which is something I did not talk about in the previous lecture. Okay, so one thing that I missed out in the last lecture is that, of course, we took different op-amp based circuits, the three commonly used op-amp circuits like voltage follower or buffer, the non-inverting amplifier, and the inverting amplifier. And we saw how the closed loop frequency response looks like, and we compared it with the open loop response, and we derived expressions for the 3 dB bandwidth or the closed loop poles of all these amplifiers. Okay, so now a few things that you guys have to keep in mind. Just we will look at these plots in a bit more in a bit more detail. So let's start with a basic block diagram representation of a closed loop system. You have a forward path amplifier, which is typically your op-amp with a single pole response, and normally we mention it with a UGB, right? If we just give omega u, it contains information both about the pole and the DC gain, right? Generally, omega u happens to be the product of the DC gain times the first pole. Okay, DC gain times the pole. And we said for all practical purposes, op-amps can be modeled as a single pole response. And for such systems, the UGB will simply be equal to the DC gain times the first pole. Now, what happens at very high frequencies? At very high frequencies, the gain starts decreasing. And at some point, the loop gain, the gain becomes smaller, and therefore the loop gain, which is A of s times beta, which is the product of the forward path and the feedback path gain, is what we are calling as loop gain. When that becomes much smaller, at that point, you have your input signal coming here, it goes through this A of s, then it's being fed back at the input port. Now, because your loop gain, the product of A of s into beta has become much smaller than 1, the quantity that will be fed back at very high frequencies will also become much smaller compared to the input signal. Under those conditions, I can treat the amplifier as an open loop amplifier, because even though there is feedback present, its value is so small that I can ignore the feedback quantity. When that happens, your transfer function simply reduces to the forward path gain itself, which is simply the op-amp's gain itself. This is a very useful point to keep in mind. Why? Because if you look, and it's even evident when you look at the frequency response graphs. So shown here is the frequency response of the open loop op-amp's response, and shown in green here is the frequency response of a voltage follower amplifier. So the closed loop gain of this voltage follower is close to 1, and the pole of the closed loop amplifier is exactly equal to the UGB of the op-amp. Now you can see here the frequency response graphs of both the voltage follower in open loop and closed loop. The closed loop frequency response exactly matches with the op-amp's open loop's frequency response. And that is because your loop gain has become, the loop gain in this case is just A of s itself. The quantity that is being fed back, beta, is 1. So A of s itself is fed back. And therefore, the loop gain, I can treat it as equal to 1. The loop gain is simply equal to the op-amp's forward path gain itself. And when this becomes much smaller than 1, which happens after UGB, right? After the UGB, the loop gain becomes much smaller than 1. I can ignore the feedback quantity, and I can see that the graph, the green curve here, shows that your closed loop response matches the open loop response. A of s is close to omega u by s. So just to I'm assuming you have watched the previous video. So A of S, the op-amp's loop, the gain is given by A by 1 plus S by omega p. So at very high frequencies, I can approximate this to, or at frequencies greater than omega p, which, since for any practical op-amp, I said we do frequency compensation, and so the first pole, the low frequency pole, it will be at a very low frequency. So for all practical frequencies of interest, especially frequencies close to the UGB, I can treat it like an integrator. So this term S by omega p will be much greater than 1. So it will be written as omega p A by S or omega U by S. So it will look like an integrator's response. So that's what I've written here. It looks like an integrator response. So the closed loop and the open loop responses will merge at very high frequencies. The same holds true for a non-inverting amplifier as well, because non-inverting amplifier just obeys this model. I mean, it's mathematical. I can just draw a block diagram representation which looks very similar to this. Okay, and the beta in this case is given by, so this is R1 by R1 plus R2 is beta, and the closed loop response we discussed in the previous lecture, the closed loop pole will be at beta times omega u. Okay, that will be where the closed loop pole will be at. After that, after beta times omega u, what will happen is that the frequency response at very high frequencies will start matching the open loop response. In a few moments, I will give a bit more intuition. So what exactly happens to the loop gain is that the loop gain becomes equal to A of S times beta, and this is the point. Beta times omega u is the point where the loop gain becomes equal to 1. Okay, the open loop gain doesn't become equal to 1, but loop gain becomes equal to 1. What matters to us whenever we are analyzing negative feedback systems is the loop gain. So that determines how much quantity is being fed back. Now after this frequency, your loop gain L of S becomes much smaller than 1. Okay, the op-amp's open loop gain can still be greater than 1, but loop gain becomes smaller than 1, and when it happens, then I can see that the open loop and the closed loop responses merge. Okay, so when loop gain becomes much smaller than 1, the open loop and the closed loop responses merge. So this is something I missed out in the previous lecture. So I thought I'll just show you guys how it happens. So I can approximate this system to a simple, I can ignore this quantity that is being fed back to the negative terminal. I'm approximating it close to 0. So if this is Vi, this is V0, the forward path gain is simply A of S itself. So therefore you see these graphs merging at high frequencies. Now similarly, just for the sake of completion, I just wanted to discuss for inverting amplifiers as well. For an inverting amplifier, the feedback model is not very as trivial, but we can still draw some intuitions. We can draw some parallels to this analysis. What I'm trying to say is that I can't draw a simple block diagram model of a feedback amplifier in this fashion easily. I'll have to put some additional term I'll have to put some additional term here before the input and then model it. So what happens is that if you guys can recall it, or let me just draw it here. So if you guys recall from the previous lecture, the mathematical model, if I draw a block diagram representation, it will look something like this. You will have a R2 by R1 plus R2, and then you will have a negative feedback system. Here there is a minus sign here, A of S and a beta. Here beta is given by R1 by R1 plus R2. Now if I use this model, you can again see that you have a closed loop model here, and this closed loop system will approximately become equal to A of S at high frequencies. Okay, when I say high frequencies greater than beta times omega u, that is the frequency where loop gain, that's the feedback path's loop gain becomes less than 1, equal to 1, and after that it will become less than 1. So when it becomes less than 1, a closed loop system will, it will almost look like a transparent system. I mean, because the feedback quantity is so small, I can ignore what's being fed back and treat it like an open loop system. Now the overall gain will be A of S times R2 by R1 plus R2. That will be your overall gain. So what you see here is that at very high frequencies, the loop gain, the closed loop response will be the open loop response times a factor. The factor is R2 by R1 plus R2. So that's what I've shown here in the green curve. If you guys see this green curve here, it is previously in buffer and non-inverting amplifier, the green curve was exactly overlapping the yellow curve. But that's no longer happening because of this factor R2 by R1 plus R2. It will more or less overlap if your gain is much greater than 1. So if R2 by R1 is much greater than 1, or this translates to beta being much smaller than 1, much smaller than 1. In that case, I can assume that the green and the yellow curves will more or less overlap, right? This factor R2 by R1 plus R2 becomes close to 1. So that's all I wanted to show. But again, one more thing I'll mention here. This is using mathematical models. You can also use Miller's theorem when you're analyzing the inverting amplifier. It's not as straightforward as the non-inverting amplifiers. So you can also use Miller's theorem, which again we discussed in the previous lectures. I can refer the input at this node to ground and model it as a resistor of value R2 by 1 plus A of S. Okay, then followed by an amplifier with a gain of minus of A of S. This is the whole mathematical model. Now, when A of S becomes much smaller than 1, okay, when A of S becomes much smaller than 1, I can treat this term, this resistance will become close to R2 itself. So you will end up getting a resistive divider of value R2 by R1 plus R2, followed by an amplifier with a gain of minus of A of S. So again, you get the same response at high frequencies. The response turns to be equal to, the response will turn out to be equal to this factor R2 by R1 plus R2 times A of S with a minus sign. Now, since we called beta as R1 by R1 plus R2, this R2 by R1 plus R2 can be written as 1 minus beta. That's it. So you can see here, if beta is much smaller than 1, if you have which means the forward path gain is very high, the closed loop gain is very high. In that case, I can approximate this to minus of A of S. Okay, so that's all I was trying to convey through this, is that at high frequencies, the closed loop frequency response of most of the op-amp based circuits will approach very close to the open loop op-amps frequency response. And that makes total sense, because at very high frequencies, the loop gain becomes much smaller than 1, which means the feedback is more or less killed. If the feedback is more or less killed, then the op-amp based amplifier will just act like an open loop amplifier. So that's something I wanted to keep in mind. One more thing I wanted to discuss was, so far when we were doing this analysis, in the previous lecture, we did a quick mathematical based analysis and showed that what will be the closed loop poles. If you have an open loop system with an op-amp with an open loop pole and a given UGB, we discussed what will be the closed loop pole and the closed loop gain of the system. We argued that if you assume the op-amp's DC gain is A and its closed loop the open loop pole is omega p, we showed that mathematically we showed gain becomes A by 1 plus A beta, pole becomes omega p into 1 plus A beta. Okay, so that's how we showed that, and using this we analyzed all these amplifiers. But as circuit designers, sometimes what happens is the open loop response becomes much more complicated. Okay, so I can't derive some simple closed form expressions for poles in this fashion. In such cases, one of the most common things that circuit designers do is to plot the loop gain as a function of frequency. Okay, sometimes we will plot the closed loop response, but more than closed loop response, we try to plot the loop gain. Okay, and this loop gain helps us a lot in designing this op-amp based circuits. Okay, so what is loop gain? Loop gain is simply the open loop gain times beta. A of s times beta will be your loop gain, and you just plot it. For a single pole system, if I assume that the op-amp can be treated as a single pole system, we can very easily predict the closed loop pole of the system from this loop gain plot itself. If you recall, for any closed loop system, the poles of a closed loop system is normally equal to 1 plus loop gain equals to 0. If you solve this equation, you get the poles of a closed loop system, right? I mean, this directly follows from the result. If you see the closed loop response of the system is given by 1 plus beta into A of s, this term is simply 1 plus L of s. L of s is your loop gain, which is beta times A of s. If you equate this to 0, that will give you the closed loop poles for this system. And all I need to do then is find out the solution for this equation, L of s equals to 1. On a frequency scale, I just have to find out the frequency at which the magnitude of this becomes equal to 1. So the pole frequency, this holds true for a single pole system. Okay, it holds true very well for a single pole system. For higher order poles, when you have more than one pole, we can't directly interpret like this. We'll have to do some more analysis. We'll introduce terms like gain and phase margins later. Right now, I'm just telling you a simple approach how to find the closed loop poles of the system from the open loop response or from the knowledge of the loop gain. So all you need to do is find out the frequency at which the loop gain becomes equal to 1. That frequency will happen to be the closed loop frequency of this amplifier. So that's what I've shown in this graph here. So on the yellow graph, the yellow plot shows the open loop op-amp's frequency response. A of s into beta. If I multiply that with beta, I get the I get the loop gain plot. This is the frequency response plot of the loop gain. So that's it. You just have to multiply this whole graph by beta. So if previously the UGB for an open loop op-amp is at omega u, the UGB of the loop gain, that's the point where the loop gain crosses unity, will be beta times omega u. And the UGB of that's the unity gain frequency of your loop gain, will happen to be the 3 dB bandwidth or closed loop pole of this closed loop amplifier. Okay, so that I can directly treat it as equal to the 3 dB bandwidth. You can do this for op-amp based circuits which don't have any frequency dependent elements, which don't have or the gain is or the feedback factor beta is not frequency dependent. I mean, I can use it for circuits like this. I can use it for a circuit with a resistive feedback, or I can use it for a circuit with a capacitive feedback. Where there are two capacitors, I can use this approach and compute the closed loop pole expression. Okay, closed loop pole for since it's a single pole system, that will also be the 3 dB bandwidth. So that's again something which is very useful. See, you guys are learning more and more stuff now. Why am I spending a lot of time on frequency response? Is because the analysis that we do here will be greatly helpful when you start designing op-amps. So that's why I'm spending more lectures on this, because it's a very interpreting and understanding frequency response graphs will make you a better engineer when you are starting to analyze or build op-amp circuits. Okay, build op-amps itself. When I'm talking about op-amps here, I'm referring to the IC design op-amps. Okay, so now using that knowledge, what we have discussed so far, let's try to find out the problem given here is that what we are interested in finding out is the frequency response of a subtractor circuit. So the subtractor circuit shown here is a very simple circuit. You guys can very easily analyze this, apply principle of superposition, and you can easily find it's a subtractor with a gain. The gain of the circuit is given by RF by R, and the output voltage will simply be V equal to V2 minus V1. It's given that RF by R is 10. The op-amp's UGB is 100 megahertz. You're supposed to find out what is the maximum input signal frequency that you can apply, okay, so that you get proper subtraction. with a gain of 10. So in other words, you are supposed to find out the 3 dB bandwidth of the circuit. Now one way is, of course, you can find out what is the frequency response for each signal. Find out the frequency response for V1, then find out the frequency response for V2. We have already done that. You know, if you ground V2, then you get an inverting amplifier. If you ground V1, you get a non-inverting amplifier. You can easily find out that we already know the 3 dB bandwidth of an inverting and non-inverting amplifiers. They depend upon the feedback network, beta, and we know what the 3 dB bandwidth is going to be. Now that we have discussed loop gain a few moments back, I want you guys to use the loop gain approach to find out the 3 dB bandwidth. How do you do that? To do that, you'll have to first short circuit your inputs. Okay, short circuit your inputs, so which means your inputs are 0. Now find out the loop gain of this op-amp. If you guys recall from our lectures on microelectronic circuits, I think it is MUE lecture 77, where we talk about, around that lecture, we talk about how to analyze negative feedback circuits. Your goal is now to find the loop gain. So first, try to break the loop at a point. So the feedback happens to be from the output to the inverting terminal. So it's of course a negative feedback. Where do you break the loop? You can assume this gain is A of S, so this is ground. So if you see, these two resistors will come in parallel, and since the current at the input of the op-amp is 0, the voltage drop across the resistors will also be 0. So I can ignore these resistors. They won't matter in the loop gain at all. So they'll just be 0. I can treat it this way. Now you have a very simple circuit that's given here. Now you're supposed to find its loop gain. The loop gain of this circuit is simply given by A of S times R by R plus RF. Okay. Now how do you find it? You can break the loop. Usually when you are finding loop gain, always break your loop at a point where there is no current drawn from that node. Okay. Whenever you find that, for example, if I break it at this point internally here, okay, I can't do that because there is no current drawn at this point. Otherwise, I'll have to do some impedances, I need to balance the impedances. So how to do that, I've discussed extensively in the microelectronic circuits course. I think it's lecture 77. You guys can go through that. But right now, this is a very simple circuit. I'll break the loop at this point and then come back to this point. That will give me the loop gain. That will be minus of A of S times R by R plus RF. Okay, this happens to be your loop gain. Now all you need to do is just plot this loop gain and find out where the UGB occurs, and that UGB will be equal to your 3 dB bandwidth. Okay, so if I call this factor R by R plus RF as beta, so this will be minus of A of S times beta. So if you guys recall, A of S crosses the unity gain point at omega equal to omega u. Okay, so if I multiply this by beta, it will just cross this point at, the pole will remain the same, but the point where the unity gain is crossed will be beta times omega u. That's it. So that gives you the 3 dB frequency. So that's what I've written here. The 3 dB frequency is simply equal to beta times omega fu. Okay, so just to reiterate, guys, I know that since we have already analyzed inverting and non-inverting amplifiers, you can directly use those results. But here I'm just giving you guys how you should think like an engineer. So we will normally look at loop gain plots and get all these intuitions out. Okay, so F3dB, the 3 dB frequency will simply be beta times Fu, and beta here is R by R plus RF. So if I take R to the denominator, I'll get 1 by 1 plus RF by R, which is 1 by 11 into 100 megahertz, which comes to 9.1 megahertz. So this is how the closed loop response for each path. The gain in both the paths are same, it is RF by R, but in one path it will be plus and the other path it will be minus. What I have shown here is the magnitude response for both the signals. So if I take VO by V1 of S, this will be the plot mod of this, or the plot will be same for VO by VO2 of S as well. Okay, the plot is same for both, And you can see for both these paths, the 3 dB bandwidth is the same. Okay, so that gives us how to find the 3 dB bandwidth of a subtractor. Okay, so far we have found out the 3 dB bandwidths for and looked at the frequency response of op-amp based circuits where the feedback network is frequency independent. Okay, it can be resistive feedback. I mean, I can just change all the resistors to capacitors. Most of the analysis will hold true. Okay, because we are using a VCVS model, voltage control voltage source model for the op-amp, the analysis that we are doing will hold true. There will be some small differences, but we will not worry about them as of now. But I'm saying that the analysis will hold true even if you have capacitive feedback networks. So that's it about the frequency response of op-amp based circuits, where the mainly we discussed about the amplifiers, subtractors and adders. In the next lecture, we will start discussing about the frequency response of integrators and differentiators. In those circuits, the feedback network will happen to be a function of frequency. Thank you.